partner, although you're not really acids and bases as lab partners, because not only are you giving information, you're receiving information to and from your lab partners. Okay, so that giving and taking should not be one way. Okay, then we also look at these pictures. So which picture best represents HCl? Is it going to be A, B, C, or D? So HA represents the acetic acid, HCl is HCl. So which one best represents HCl? A, B, C, or D? A? Why A? Yeah, well, HCl technically is not an ionic compound because there's no metal. But we know that HCl, when it reacts with water, can donate a proton to the water to form H3O plus and Cl minus. And the shortcut way of writing this is HCl aqueous goes to H plus, aqueous plus Cl minus. Okay, so this is the shortcut way for writing this. So when we show the dissociation of HCl, we can write it this way. So diagram A represents the dissociation of HCl because HCl is what type of acid? And the strong acid is defined as something that does what? Yeah, so donates its protons. So you should see a lot of protons in solution like you see here. For acetic acid, which diagram best represents acetic acid? D? You guys agree? Should it be D? Okay, yes, it's D. Which statement is true? 0.1 molar HCl has a higher H plus concentration than 0.1 molar acetic acid, or is 0.1 molar HCl has a higher pH than 0.1 molar acetic acid? So which one is true? So who says statement 1 is true? Okay, so you guys know that already. Okay, so as a further review, we know that bases undergo hydrolysis. So a base, which is represented by A minus, reacts with water to form HA and OH minus. The equilibrium constant for this reaction is called Kb, B for base. That's equal to Kw divided by Ka. We can look up the Ka in table 16.3 or 16.4. We know that Kw equals 1 times 10 to the minus 14. We also know that bases can be either strong or weak. So which of these 5 statements is true? Okay, so one way to answer that question is go see eeny, meeny, miny, mo. That's not the best way to do it. So what statement is true? Is statement 1 true? Weak bases accept H plus more easily than strong bases? No? Okay. What is statement 2? Weak bases have a lower Kb than strong bases? Yes. Yeah, so what statement 3? NaOH is a weaker base than NaC2H3O2. What's statement 4? 0.1 molar NaOH has the same pH as 0.1 molar NaC2H3O2. And what was statement 5? True or false? Okay. Then we also did this on Tuesday. To calculate the pH of a weak base, we write that base hydrolysis reaction, look up Kb, or recalculate Kb based on Ka. We can do another equilibrium calculation to calculate the OH minus concentration. Once we know the OH minus concentration, we calculate POH. Then once we know POH, we calculate pH. Okay, then we talk about buffers. Now we can look at a buffer in terms of a titration curve. So this is our titration curve. At this point here, we have acid only. No base has been added in the titration yet. As we add base, the pH increases just as slightly. Then all of a sudden, it increases a lot. And this inflection point is considered the endpoint. So you can actually use math in calculus. What is that? That would be the, is that the second or the first derivative of that function? I can't remember. First? Second? Yes, that inflection point. So that inflection point, we'll actually do this in lab next week when you measure the titration curve, so you can look at the Ka values of milk. You'll actually take the first and second derivative of a titration curve, and based on that, you look at where the endpoint is. Okay, so you'll do that in class next week. So anyway, here's the endpoint. At the endpoint, what substance is present? Okay, so HA is reacting with the base. So at the endpoint, George, what substance is present? Yeah, just the base. Okay, so all of the acid has reacted at that point. Only the base is present there. Then at the halfway point, what substances are present? Yes, you have half of the HA and then half of the conjugate base present. Okay, and then we know also at the halfway point that pH equals pKa according to this equation here. Okay, so when A minus equals HA, that's equal to 1, so log of 1 equals 0. Therefore, pH equals pKa. Okay, then we also looked at this. We used this equation to make a buffer. And we followed these 4 steps to figure out which acid to use and how to make that buffer. Now, note that at the halfway point, A minus equals HA. Before the halfway point, what's true? A minus is less than HA, A minus equals HA, or A minus is greater than HA. Okay, so is it 1, 2, or 3? Okay, so looking at the titration curve, here's the halfway point. So before the halfway point is in this region here. So is it going to be 1, 2, or 3? Or if you like watching The Price is Right, is it behind door number 1, behind door number 2, or is it behind door number 3? So sometimes I even feel like a game show host standing up here, staring at this big audience, trying to see who's going to be the winner today. Yeah, great, great. Okay, so to help you answer this question, let's write one more equation down here. Okay, so we have HA. This is our acid. This reacts with the base. This says that the base is OH minus. So what are the products of this reaction? Yeah, so we know that H donates a proton to water, so it's going to be H2O and A minus. Okay, so let's just say, we'll make up some numbers. Let's say initially you have 10 moles of HA. Okay, you haven't added any OH minus yet, which means that there's no H2O and A minus forming yet. Okay, so let's say now you start the titration. So when you start the titration, you've added 1 mole of OH minus. How many moles of HA reacts with it? Okay, 1. How many moles of H2O are produced? How many moles of A minus are produced? And then, at equilibrium, or what's left over, how much of the HA is left over? Okay, so we have 9. And how much OH minus do we have here? Yeah, because none of it, we should have none of that because all of it has reactants. How much H2O has been produced? Okay, 1. And then here's going to be 1. So on the titration curve, we're somewhere in here. Okay? So as we continue to add more H2O, now let's say we have 2. Okay, so now you've added 2 moles of OH minus. How much HA reacts with it? 2. How much HA is left over? 8. How much A minus is present in the solution? 2. So now we're over here. Okay, so we're creeping toward the halfway point. So note that what we're looking at is we're looking at the amount of HA compared to A minus. Okay, so when we get to the halfway point, how much OH minus do we need to add to get to the halfway point? Yes, we need 5 of these. And how much of these is going to react? Get 5, and then how much of this is going to be? Get 5, and how much A minus is? Get 5. So now we're at the halfway point. Okay, so you're seeing the pattern here? So the answer to question 1, before the halfway point, it should be, which one? 1? Yeah, because note that what we're doing there, HA should be greater than A minus. Okay, so it should be 1. After the halfway point, what should it be? It should be 3. Now, when you're doing your buffer calculations, you should see the same thing. So for example, let's say this is the titration curve for acetic acid. Now, what is the pKa of acetic acid? Okay, so here's the Ka of acetic acid. So pKa is equal to minus log of this number. And I think when we did the calculation, that pKa turned out to be 4.7. Okay, so for acetic acid, right here, at this point here, the pH is going to equal the pKa, or 4.7. Now, if you want to make a pH 5 buffer using acetic acid, note that you're going to be somewhere right up there. Okay? So at that point, are you going to need more of the acetate ion or more of the acetic acid? Okay, so you're past the halfway point, and when you get past the halfway point, that means you need more of the acetate than the acetic acid. So this is what that Henderson-Hasselbalch equation is telling you. Okay, then also with the buffer capacity, so let's just say you have a pH 5 buffer here. If you add base, note that you creep toward the steep part here. So with your buffer capacity, you add base, all of a sudden the pH shoots up. When it shoots up, then you've exceeded the buffer's capacity. It is no longer going to buffer or resist change in pH. And then if you add an acid, note that the pH will drop a little bit, but in this case here, you're fine. Okay. Now, note one thing about buffers is that it has to be a weak acid and its conjugate base. And what is the reason that a buffer has to have a weak acid and its base present in solution? So if you have an acid and a base present, if you add a base, what's the base going to react with? Yeah, the acid part. If you add an acid, the acid is going to react with the basic part. Okay, so this is what you can be doing in lab today. So there's chemical reactions that produce the color and smell of grilled meat if you like your barbecue. You'll be doing this middle one today. Fruit turning brown. This is caramelized sugar. So there's actually 4 types of browning reactions. One is the Maillard reaction. The Maillard reaction is what turns meat brown and gives it that smell and flavor. And that's due to the reaction of sugar and an amino compound, which is either an amino acid or protein, that produces aroma, flavor, and color. So this is a, at least from my mind, a very important reaction. Another one is caramelization reaction. So this is what's happening. You have caramelized sugar. So you have to take sugar, you heat it up to a certain temperature. It turns that caramel color and also gives that caramel flavor. Okay, so that's the caramelization reaction. Again, only sugar is involved there. Vitamin C also oxidizes to a brown color. Have you heard of brown orange juice? Although it's sort of sometimes hard to see that brown color in orange juice because it's already orange.